the meninges. Right? Those three membranes, we call the dura mater, the pia mater, and the arachnoid mater. And basically the same thing we talked about before applies here. So I'll give you all the details here. You can see some pictures. It's not a picture of us again in any kind of lab exam or anything like that, but it basically goes and shows you where that fits in the brain, and you can see that it actually goes even within the fissures of the brain. We're not going to get into the details though. As you can see here, some more details about that. Now, the brain that you have today, meaning the sheep's brain, the bucket that I grabbed does not have the dura mater on it, the glass. It is very, very thick, and you can kind of see that in the picture right here. As I said, it's very much like a rubber glove, so you have to sit there and cut it. But the bucket that I grabbed is all removed, I think, so you should be able to go right into the brain and have some fun. So, don't worry about that, right? So your brain looks like this, a lot like that. Okay. I mentioned all this before. This is a nice picture, though, that this shows you the movement. The movement of the cerebrospinal fluid. So the cerebrospinal fluid is what holds the brain up. About 97% of the weight of the brain is actually supported by the cerebrospinal fluid. You can see the brain kind of sits within the cavity and floats within this fluid. And you can see the movement of the fluid is predicted by these lines. It goes around the brain, even down the cord, and even goes into the ventricles like we talked about before. So this is the choroid plexus right here in red. We'll come back to this in just a second. But this is actually what makes the cerebrospinal fluid. So it gets made from capillaries. So this is a better picture of that choroid plexus. So cerebrospinal fluid is basically plasma, blood plasma. It's a little bit different in its composition. It doesn't have everything that plasma has in it because there is what we call blood-brain barrier, which we'll talk about in just a little bit. But for the most part, you can imagine that this is a capillary right here, a blood vessel, and we're going to have the filtrate, or the plasma, come into the brain cavity, which is what you have here. And so you have your ependymal cells, and you have some other cells, astrocytes, and some others that play a big role around here, and basically making sure that only the cerebrospinal fluid or plasma comes through, and other things are added to it, and it becomes what we call CSF. So this is the choroid plexus. This is what actually makes it. So there are capillaries within the brain, areas within the brain that are rich in capillaries, and that's the area that is responsible for making the cerebrospinal fluid. And so when you cut into your brain, you're going to be like, you'll cut into it sometimes, and you'll see this very, very darkish, rusty-looking little glob. You're like, what is that? It's the choroid plexus. Cut into it. Found it. Okay? So that's what you're going to see later on today. Blood-brain barrier, or BBB. Blood-brain barrier, page 28. The brain is composed of neurons. And neurons need two things. They need glucose and they need oxygen. And so, big surprise, there's really no hindrance to bringing in glucose and bringing in oxygen from these capillaries. But other things are not needed, at least not readily. And so very few things can go from the blood vessels, let's say the peripheral body, into the brain. It's restricted. And specifically the way it's restricted is by having these cells be very tightly connected to each other, whether they be ependymal or astrocytes. There's really a lot of astrocytes that play a role here. But you have a very tight connection, so that the only way something can go from here to here is to go through those cells. You can't go in between them. They're very, very tightly knit. Does that make sense? So really, the majority of things that go through are things that either have a channel, that have a specific lock and key channel, like glucose. We have a dedicated channel to bring glucose across, a glucose transporter, or it's things that are lipophilic, that love lipids, that are lipids themselves, that are non-polar, in other words. So your fats and things like that can go through into your brain. Or certain things that are composed mostly of fats, like certain chemicals or certain drugs that you take, medications, that are very lipophilic in nature, there's not many of them, but there are, can go through the blood-brain barrier. Other things are not easily transported. And so if you're in a world that I'm in at Lilly, we work on drugs, medications, and sometimes we want to go into the brain, and sometimes we don't. And so drugs have to be designed to be either more lipophilic or lipophobic, as you say, to get the desired function. The blood-brain barrier serves a very important role, because let's say, for example, you have a toxin in your blood. You don't want that to go in the brain. You want to protect the brain at all costs, the brain and the spinal cord, at all costs. And so you're going to have a very, very tight leash on what you let into the cerebrospinal fluid. Just that you can have all kinds of issues if it's bacterial in form in nature. You get meningitis or toxin can obviously kill the brain, and you can't regenerate it. We talked about that. Once you kill the cells, they're gone. So BBB, or blood-brain barrier, is very important there. Now, there is one place, though, you don't have at least, let's say, 100% coverage. There's some part of the brain that you only have partial coverage with the blood-brain barrier, and that's the hypothalamus. So what is the hypothalamus again? Well, it's that detection area, or it helps control various parts of the body. It's the autonomic control center. So let's say you have a poison. Let's say you ate something bad, and it had some kind of toxin in it. That toxin goes into your bloodstream from your stomach, from your intestines, and it doesn't get sensed by the brain. The brain doesn't pick it up because it doesn't go through the blood-brain barrier. But the hypothalamus does, because the hypothalamus is partially exposed. And guess what the hypothalamus does? It makes your stomach upchuck. It makes you vomit. Right? It's the autonomic control center. It's going to do something involuntarily. In this case, you're going to puke. You're going to throw up to get rid of the toxin. So we do have portions of the brain, like portions of the hypothalamus, that are exposed. They don't have full coverage through the BBB, and that's the reason why. Homeostatic imbalances. I'm not going to ask anything specifically about this. If you're just interested in this, you can see it. Alzheimer's, Parkinson's, Huntington's disease. These are all things that are degenerative diseases of various portions of the brain. Some are unknown causes, and some unknown reasons, like plaque formation in the brain. It's unknown whether it's a cause or effect with Alzheimer's. Time will tell. You're good at that. Parkinson's, Huntington's disease, they know the parts of the brain that have degeneration. They don't really know how to correct those things. They can only do some things to slow it down. We'll leave it at that. Cranial nerves. This picture right here, and actually I brought this for a reason. Let's see something real quick. Yeah, so I don't know if you looked at the third lab exam details that are online, but there's only 5 things from this figure. And this is the figure, by the way, that tells you right here, figure 14.27a on your exam. There's only 5 that you still have to label. But there's actually 12 different cranial nerves. And you should know these 12 cranial nerves, okay? At least by name. I don't care much else. I'll tell you specifically what I would expect in just a few minutes, okay? But I wouldn't expect something crazy like abducens. I wouldn't expect you to know the abducens muscles control, among other things, the muscles of your eye, because you're going to find out 3 or 4 others do as well. Okay? But when you get to the optic nerve, you should know optic is involved in vision. Okay? That's kind of obvious, but just so you know. Okay? Or olfactory is involved in smell. So these are them. They are numbered 1 through 12. So first and foremost, we have 12 cranial nerves. We have 31 spinal nerves, 12 cranial nerves. 12, 12, 12. Right? 12 cranial nerves. And their name: olfactory, optic, ocular motor, trochlear, trigeminal, abducens, facial, vestibular, cochlear, glossopharyngeal, vagus, accessory, and hypoglossal. Now, a lot of those terms are similar with respect to the letter they start with, and that's what's going to make it a little bit complicated for you to remember this. But there's a nice mnemonic device. It's this: on old Olympus towering tops, a friendly Viking grew vines and hops. So if you look at that, you say, okay, on old Olympus towering tops. So olfactory, optic, ocular motor. So if you start here at the top, or the front, you can start to name them as you go down, and that's what this is. So olfactory, right here. On, Old Olympus, okay? Olfactory, optic. So there's the optic showing the eyeball, okay? Ocular motor is right here. It's the next one. And so on and so forth, all the way down. On Old Olympus, towering tops, and for anybody who binds the tops, okay? There are other ones on the internet, but they're more crude, so you can go look them up yourself. This is the one I like. So, as I said before, you can have mixed nerves, or you can have motor nerves or sensory nerves. Okay. Now, in the spinal nerves, they're all mixed, but in the cranial nerves, they're not. Some are motor, some are sensory, and some are mixed. If you had to know this, and you don't, if you had to know this, you can go through the same list on Olympus Towering Tops and apply this mnemonic device. Some say marry money, but my brother says big brains matter more. Again, there are other ones. But if you had to know that, you can say, okay, some say. So that means olfactory is sensory. Optic is sensory. Ocular motor, right, is motor. And then some, of course, say are B, which is both. So if you had to know this, which again you don't, that's the way you do that. Use it for future reference if you want to. Okay? So let's go ahead and look at some of these. Again, on your lab exam, you have to know a couple of these, and I'll point these out, the ones you got to know. So first is olfactory bulb, or olfactory nerve. Okay? So this is actually right here. So olfaction is smelling. So this is the olfactory nerve, and this is actually what they call olfactory bulb right here. You'll see a better picture in just a few minutes. So smelling. When you look at your sheep's brain later on, this is huge. Why do you think that's huge? What do you think sheep do all day? They smell. They have a nice sense of smell, like a dog. Right? Maybe not quite as adept as a dog, but they have a better sense of smell than we do. And so these are very highly developed, very large in a sheep, who spends all their time searching for that perfect blade of grass, right? So that's the olfactory nerve, or olfactory bulb. Don't think about it, okay? Optic nerve. This is the optic nerve right here. And you can see that it connects to the eyeball, okay? Now what I want to point out here is this crossover. See the optic chiasm? They've already cut this here, but this is the other eyeball up here. So this connects here, and this connects here, and you have a crossover, or chiasm, optic chiasm. This is something that's going to be real hard to understand right now, but you'll understand it better when we get into chapter 16, which is next week. Okay? But some of the fibers that come from this eyeball go this way, and some of the fibers go this way. So in other words, some of them go to your right hemisphere, and some of them go to your left. Some of the fibers coming here go to your right, and some of them go to your left. And you're going to see how that separates. But in general, it makes sense. Your right hemisphere is seeing the left side, and your left hemisphere is seeing your right side. But if you look, let's say look straight ahead, right? If you look at both, when you're looking at directly in your peripheral vision, when you're looking at things over here, are you seeing everything over here with just this eye? No. You're seeing it with this side too. So the portions of this side that are seeing things on this side, and this eye that's seeing things on this side, all that's routed toward this side. Sorry, the opposite. You'll see that. That's optic chiasm right here. Okay. The vagus nerve. Vagus nerve is right here. The vagus nerve is quite different than other nerves of the cranial nerves. All of the other nerves of the cranial, called the cranial nerves, are for the neck or face regions, the head. The vagus nerve actually communicates with the, well, we'll see in a minute, a large percentage of the visceral organs, involved in a lot of sensations and perceptions from the intestine, among other things. So that's the vagus nerve right there. And the vestibular coccygeal nerve. Okay? That's right here. Okay? The vestibular coccygeal nerve is involved in hearing and balance. You'll see that in just a minute as well. So these next pictures are not going to be on your exam, but I just kind of show you some examples of these. So again, here's the olfactory bulb, and here's the olfactory nerve involved in olfaction, which is smelling. And so here we're bringing in a nice odorant from the room, It's dissolving in what we call the nasal mucosa. We'll learn this later on. And that information is relayed up here to the olfactory bulb, which is relayed here to the olfactory tract, and brought over to the olfactory cortex, which we smell. We can understand the perception of smell from that. Obviously, the optic nerve involved in vision, in the sense of vision, the sense of seeing things. Now for some ones you wouldn't have to know. So you should know optic, you should know olfactory. The ocular motor, it's one of three that actually controls the muscles around your eyeballs, among others. So ocular motor, one of those here. We also have trochlear, and those have uses as well. We'll get to it in a minute. Trigeminal, among other things, it helps you chew. Involved in mastication, chewing. Again, I would never ask that. It's a small little thing. Same thing with abducens here. Again, another one that controls movements of the eye. Again, think face, think neck. So we're having here movements of the eyeball. Facial. Among other things, it helps control the tongue. It helps produce saliva and salivary glands. It helps produce tears. Again, nothing I'm going to ask you specifically, but that's what this is about. The facial nerve. Vestibular cochlear, one you should know. Vestibular cochlear. We're going to learn more about this later on. This is not a picture you're going to have per se, but a very similar picture will be from chapter 16. When you talk about the ear, and specifically this part of the ear we call the inner ear, okay? We have two portions here. The portion right here is called the cochleate, and it's involved in hearing, the actual sense of hearing. But up here, the semicircular canals and a portion right here, which we're not going to get into right now, are involved in balance, equilibrium. And so we have one nerve that sends impulses from both equilibrium and hearing, and it's called the vestibular cochlear nerve. Glossopharyngeal, again, tongue, saliva, among other things. And here's the vagus. By the way, you don't have to know the Roman numerals that apply to this, but they're named by the Roman numerals as well as their names. It's one of the names that I would expect you to be familiar with. So this is the vagus nerve. This is the one I said was atypical of the other 11. Because this one doesn't just communicate with the face or the neck, it actually communicates with the rest of the body. You can see there's actually connections with the heart, with the lungs, with the liver, with the stomach, with the intestines, the kidneys, spleen. And all these different tissues are connected with the vagus nerve. And again, you'll learn more about this later on. I'm not going to get into this now. Okay. Accessory helps move your neck, muscles, things like that, helps move your neck. Hypoglossal, swallowing, talking. Again, one I wouldn't ask per se. Again, on page 34, you'll see that right here at the bottom. Really small print, so I can save one page, so I would do 42 pages instead of 41. That's where that big picture is. Laugh it up, right? Okay, so that's all I had for the brain. How are we doing with the brain? Brain fried? Yeah. This last part, again, chapter 15, we'll start on page 35. 90%, roughly, 80, 90% of your exam will be from chapter 15. Okay? In fact, none of your lab exam will come from chapter 15 at all. It's just from chapter 14. Okay? And it says that already here. If you actually look at the things here, it even tells you all that, what's actually on your lab exam. Okay? There's nothing here at all in chapter 15. It's just from chapter 14. And then it goes straight into the eye, the ear, etc. Okay? So that'll be chapter 16 we'll talk about next week. So, but chapter 15, you do need to be familiar with for, let's say, one or possibly two questions out of 10. So 10 or 20% of your lecture exam will come from this. The lecture quiz, I should say, will come from this topic. And in general, you can probably guess what the questions would be. Big picture kind of concepts. But let's go ahead and go through this material. So chapter 15 is the autonomic nervous system. So let's go ahead and review that real quick. So we already talked about the fact that the nervous system is composed of two different parts, the central and the peripheral nervous system, and you can see that here now. So the central nervous system, again, is the brain and the spinal cord. The peripheral nervous system is everything in yellow. So the nerves and the ganglia that are right here are all considered part of the peripheral nervous system. Right? Another way of looking at it is, again, central nervous system, and then we have our peripheral nervous system. In our peripheral nervous system, we can divide this into sensory and motor. Sensory and motor. And we talked about this in greater detail, but sensory division right here would be vision, hearing, right? Sound. So we'll talk more about that. And the visceral will be, stomach ache, full bladder, things like that. That would be the sensory division. Motor division. Somatic motor division is the voluntary motor division. So we voluntarily move our muscles, right? Our skeletal muscles. The visceral we haven't really talked too much about, specifically because it covers this and this, which are kind of complicated, and I said we'll cover it later. Well, here we are. The visceral motor division is going to control everything that we don't have conscious control over. For example, heart rate, or breathing, at least, well, yeah, a little bit. Blood pressure, right? How fast we digest food in our intestines. These are things that we don't really consciously control, right? But our body does it. Our body makes decisions all the time. Where am I going to put my energy? Where do I want to put energy toward moving my muscles? Or do I want to put energy toward digesting that meal that I ate? And it can do both at the same time. Or it can change the balance and put more energy toward one thing and less energy toward another. Okay? So it's always an energy balancing act, and that's where we're going here, is this energy balancing act. So you'll see we divide this into what we call sympathetic and parasympathetic. Well, the easy way, in other words, if I were to explain this to my kids, this is how we'll start off, because a lot of people start off this way, is okay. Think about the sympathetic division like this. Fight or flight. Fight or flight. What does that mean? Well, if you're getting ready to fight somebody, or you're getting ready to run away, then your body is gearing up toward that. It's going to increase blood flow, for example, to the skeletal muscles, to the heart. It's going to raise the blood pressure. It's going to raise the heartbeat. Because all these things are important to either fighting or running away. One of the two, right? It's a fight or flight response. So if you're getting ready for something like that, then your sympathetic motor division would become active. And the neurons that would communicate with your heart, that would communicate with your blood vessels, would change, would cause some sort of dilation of the blood vessels, for example, or increased heart rate. Make sense? This one is called the rest and digest. Rest and digest. This is the couch potato effect. This is the, I'm not trying to get away from anybody. I'm not trying to fight anybody. I'm going to sit and relax. Okay? No, it's not Monday Night Football, right? You're, oh, stupid. Just kidding. It's the nice, relaxing Hallmark movie, right? Maybe not too emotional when you're Hallmark movie, bad example, but it's nice and calming, right? And this is where we're going to devote a lot of our energy toward digesting it. And so we're going to, instead of bringing blood to our skeletal muscles, we're going to divert the blood to our intestines. So now our energy, our blood, and everything else is going to be spent digesting our food. So would it surprise you if you're running a marathon if you're not actively digesting your food? Well, no. It makes sense, doesn't it? Your body's saying, I need to use the energy to run. I need to use the energy to run. Why process your food now? Let's do that later on. Right? That's what your body is doing. So you're not actively producing urine very easily or very readily, although you're doing a little bit. You're not actively digesting your meal as much as you would be if you're sitting on your couch. So we call that sympathetic and parasympathetic. And again, they're kind of opposites. Kind of opposites. the main focus, or the main purpose of the autonomic nervous system, it's been called, we call this, okay? Or the involuntary nervous system. The whole point of this is homeostasis. It's all about homeostasis, right? And a good example of that would be what we call a visceral reflex. Okay, a visceral reflex. So what a somatic reflex we've already talked about. That's like the tenon reflex, where you hit and you kick, right? That's somatic. It's the voluntary muscles. But here we're talking about internal, something involuntary, something that is visceral. So a good example is blood pressure. What do we do if our blood pressure goes up or goes down? Well, we have to respond to that. And this is one example of how this can occur. So this is the carotid artery right here. And we have receptors. They're called baroreceptors, and they basically detect changes in pressure. Baro just means pressure. So baroreceptors, it's a receptor, a neuron, which feels or senses with its dendrites stretching. So it feels stretching around this artery. And when that gets stretched, it fires. Its neuron fires. And its synapse is right here. This is actually the medulla. Okay? It has a small interneuron right here. And then it goes directly back over here to the heart. And it causes the heart to reduce its heart rate. And so if your blood pressure gets too high, you have a reflex that will automatically reduce your heartbeat. Notice you're not going to the brain. Here's at least not what we call the conscious brain. We're simply having a simple reflex. Very similar to what we described before. To maintain homeostasis. To maintain steady, constant blood pressure. The same thing, or a similar thing would occur, for example, you've probably done this, right? You're sitting down for a while and all of a sudden you stand up really quickly. Anybody ever get really kind of dizzy for, you know why that happens? Because your blood pressure drops like a rock. Okay? You have to have a way to build up your blood pressure again. And a similar response happens, a reflex happens, to build up your blood pressure. To raise the cardiac rhythm so you can build it back up so you don't fall. Okay? So as I said, if you were to divide the involuntary nervous system into two parts, it would be sympathetic and parasympathetic. So the two big words to remember are those two words, right? Sympathetic and parasympathetic. Sympathetic, again, fight or flight. Parasympathetic would be rest and digest. Now, what people often confuse, though, is they always think about this as being one extreme or the other. And this is not true, okay? The truth is they're both working at the same time. So if you think about this division has neurons, and they're constantly firing and releasing neurotransmitters on the heart. Think about it that way, right? So here's your heart. And it's receiving fibers, neurons, right, from the sympathetic nervous system, which is causing it to beat faster, okay? It's also receiving stimuli from the parasympathetic division, which is saying beat slower. And so they're both working in concert, okay? So they're both working it all the time. The only difference is sometimes this will work a little bit more than this one. So it's not like a one is on and one is off situation. It doesn't work that way. One is higher than the other, and it's a balancing act. And so to think of extremes is, well, not true. Okay? That's a lot of what happens in elementary. When you teach kids this, they think, oh, it's an all or none kind of thing. It's not. It's often very subtle, very, very subtle things that can happen. So you may be in a sympathetic response, where your sympathetic nervous system is working better than your parasympathetic, and you barely notice it. Barely. It's not like you're all of a sudden tense and rigid and you feel like you need to run a mile. It's not like that. It's just a small little, keeps you attentive, for example, in class. Okay? So both are active, is my point there. I'm not going to get into all this other stuff here. I'm not going to get into all this stuff here. Let's see what I'm going to mention. I'll mention this just because I think it's somewhat interesting. I don't have a good picture of it here. So this just shows you this right here and this right here. What I want you to see is this is the sympathetic. Yeah, this is a sympathetic nervous system. So this is